All right, everyone. Welcome to the Allen School Colloquium. Today we have a treat especial. Andres is here from MIT to tell us how we can have our cake and eat it too. And by that, of course, I mean have correct software which is also performant. So please join me in welcoming Andres.
Yeah, thank you. I'm here to tell you about building cryptographic software and cryptography adjacent software with proofs in a manner that meets the needs of real-world adoption. And in particular, it is towards this larger vision to build and maintain systems with proofs for applications where correctness is actually critical. So this perhaps could be broadened further to computing at large to verify common infrastructure underlying many systems, but I'm talking about specific, small, high priority components today. And in particular, I took this workflow where I study what experts actually do. I go and meet with the cryptography implementers and study their techniques, not just their code, but how they produce it. I then encode their reasoning in a computer proof checker, in my case Coq, and prove it to the higher standards of rigor in general. From this general system, I produce code that actually gets deployed into real products and serves billions of users every day. All this is a part of a larger software ecosystem where we prove adjacent components against specifications that meet each other. So we prove small components of the entire infrastructure of the internet, but by proving adjacent components, we have this property where the specifications of adjacent components cancel out, where we can derive a larger proof about the combined behavior of those components that minimize the risk of specification bugs, which is the topic I will return to at the end of this talk. Now, what is a computer-checked proof? Well, you have a software into which you can write statements, perhaps like this high school algebra identity over here, and then you can write proof script steps where you ask the system to manipulate your proof goal, in which case this simple step of simplifying with ring rules already achieves the desired goal, and then when you're done, the system actually checks that your proof showed what you claimed to show. The same can be done with programs. Here we have a simple program that takes in 2 memory addresses and loads from those addresses and swaps the values by writing it to memory. For this, giving the specification is a little bit harder because we need to have an implicit understanding in this proof system of the programming language in which this program is written. And then we need to write a specification that, in the case of this language, talks about memory locations. It says that memory location A contains the value of A, and then afterwards it contains the value of B. For simple programs like this one, the proof can again be completely automatic, but we'll soon get to programs where achieving automatic proofs is much more challenging. And underlying all of this is a definition of what is the meaning of executing a function in this language, which I would argue is still an active topic of research where advances can have significant real-world impact. Now, the agenda for today is to first talk about cryptographic implementations, specifically fiat cryptography and cryptopt, which are the tools behind generating high-quality elliptic curve cryptography code for web browsers and operating systems today. And then talk about integrating proofs of separate components into system-level theorems and the unique benefits this approach has. Now, jumping right into fiat cryptography, on this slide is a sample of real-world assembly code that is still in deployment in some circumstances that computes modular multiplication modulo a particular prime number. Now, first, to just understand what kind of code we're looking at here, this is a Perl script that prints an assembly file. It would be even longer than 4,000 lines if it was actual assembly. In the comments of this code, there are details about how it was optimized, but not all of those comments make any sense because they refer to details about how the processor works that have never been described in public documentation. We also see artifacts of compiler-style optimizations that programming language people know very well, where some loops have been unrolled and there's some pipelining going on, but all of these have been applied manually because some other parts of the same code are outside the fragment of instructions that compilers can make efficient use of. For example, they use instructions that set both normal registers and flags in one step. And the implementation here, or some of the lines below that are less instructive, were the subject of a rather scary bug in OpenSSL where the wrong numbers were computed, effectively likely breaking all cryptographic guarantees in practical applications of this code. And while there was a strong effort to audit this code, I have not seen anybody who would claim that they have high confidence that they found the last bug. They just found some bugs. And this is a real challenge because this is not the only implementation of this kind. It's not just the 100 lines you would see on the screen or the 4,000 lines below that. Is that this effort gets repeated manually by top experts who are really good at doing this for every operation. So this was multiplication. For every prime modulus that is in common usage, this separate piece of code gets written for performance and security reasons. And then for different generations, even different generations of Intel processors, we have separate implementations that achieve better performance than the one optimized for the previous generation. And all of this is a lot of work, and it takes a lot of training to get good at this. And thus, everybody who knows how to do this already has a long backlog of operations where they would optimize and audit. And there is a fundamental trade-off between achieving more performance and thus deploying cryptography more widely and achieving higher confidence in the existing implementations. And this is really the trade-off that I chose to tackle and try to reduce or almost eliminate with my work. Now, just to look at what the bugs are like, well, in the code that I showed you before, there were some comments saying it doesn't overflow. Unfortunately, some integers did overflow. And this computed the wrong answer mathematically, even though it didn't lead to any obvious safety issue in the programming language. Now, the explanation for why this bug happened was that somebody got math wrong. The concept was good. One could have written a correct implementation based on the strategy, but accounting for the bounds of those integers just went wrong in the implementation process. Once it was fixed, the new implementation was endorsed with the high praise of good for 6 billion random tests. And in a different case, there was a typo, and R1 should have been an R2. Again, it was in the middle of thousands of lines of pseudo-assembly code like this, and this was found through a serious human auditing process by a group related to the maintainers of this original implementation. So the people really do care about correctness. It is just really hard to get it right. And for the second bug, it was actually later reasoned that random testing would not have helped. Like the probability of triggering the bug is very small in random inputs, whereas a malicious input might still be able to trigger it. Now, I went through bug trackers of popular cryptography libraries and categorized the bugs that had serious security consequences. And bugs in mathematics implementation like this are really the bulk of really serious issues. So I chose to build a system that tackles this. And in particular, I took a compiler's approach to it, where we say we want an operation, say multiplication modulo the prime that is on the screen, and then low-level code would be generated. And in Fiat cryptography, the tool that I built, this code is produced automatically from an input that I will soon discuss. But regardless of how the code is produced, all the steps together are proven correct. So both the input to the code generation process and each stage of the compiler are proven separately and then tied together to one correctness theorem. And the generated code runs essentially as fast as what an expert would have done in a similar language. So the C code we generated at the time was competitive with the best C code for the implementations it was benchmarked on, and so on. At the input of our compilation pipeline is actually functional programs. And it is really counterintuitive that you would write a generic functional program that operates on lists of different positions representing a large number, and then achieves competitive performance in spite of that. But we'll see how it actually falls out very naturally in how those algorithms are expressed in Fiat cryptography. It is also an active Coq project on GitHub, and we have received excellent contributions from both cryptography engineers in industry who, in some cases, learned Coq to contribute to this library, and from undergraduates that have been able to ramp up at an impressive speed and get amazing results within this framework. As a result of this, Fiat cryptography is used in a number of popular projects, such as web browsers, operating systems, cloud services, and security libraries. And for some of these companies here, security is really a core aspect of their business. So them investing in Fiat cryptography is a high endorsement of the quality achieved through this means. Taking a step back about what was going on here is that I studied how experts produce this code, and then I found a way to express the same code as a combination of simple functional programs and simple compiler optimizations that produce sophisticated high-performance code. But this decomposition drastically simplified the process of proving this code correct. Without this, we probably would not have been able to prove the large number of implementations so far generated by Fiat cryptography at all. While mimicking the generated code that experts write by hand led us to achieve good performance with high reliability. Essentially, anything you could do without Fiat crypto, you could probably do with Fiat crypto. And really, the unique aspect about the approach here is that we started from how experts do their work. Now, At the top level, as we have said, there's a specification that says we compute A times B mod M, and then we write the functional program. The one over here is actually a real one, but we will look at this in a moment more. We prove them equivalent, and then there are some compiler stages. I will now just walk through what the steps are. First, we need to pick parameters for this very generic functional program that acts as a template for the implementation. The parameter choices themselves are not verified, but it is not important to verify them because we prove the template correct for all possible parameters. Then the template gets specialized by a certified compiler, producing code that is specific for those parameters and is much more efficient than the original, after which we can replace the template's operations on mathematical integers with operations on machine integers, so int32 or so on. And finally, there is low-level optimization at the assembly level that is performed by the CryptoOp tool, which I'll also briefly discuss in a moment.
You mentioned that you don't need to verify parameter selection. This is like the prime that you're using for that field, or?
So the prime is a part of the specification. So yeah, we don't need to verify it, but it is what the user asks. There are also other parameters that are only relevant to performance, such as how many positions you use to represent one number modulo that prime. Yeah, and there are others like this where experts know how to pick good choices and sometimes discuss them in their papers, and our templates take them as arguments, and there are some heuristics to fill them in automatically in case that is desired. And then the proofs of the individual phases are brought together to a single coq proof that relates the top-level specification in terms of mathematical integers to the actual generated assembly code. Now, I'll show you what one algorithm in this space looks like, first in normal mathematical notation, and then in how it works in our system. But just to give you a background of what we're talking about here, we have representations of integers that might be hundreds of bits long using a handful of machine integers that are 32 or 64 bits long. We might not use all 64 bits of each machine integer. And then we choose the representation so it matches the primes we use. We want our position in our representation to be very similar to the prime. There should be a small difference c that is explicitly accounted for. And the c could be literally a small number, or it could be a sparse number that has only a few bits set. Or it could only be possible to find a small c if you use different numbers of bits in every position of your representation. And all of those tricks have been discussed in cryptographic implementation literature. And these three tricks will be achieved by one fiat cryptography template that generates code for all of these three implementation styles and thus achieves decent implementation quality for a large number of cryptographic applications, or perhaps acceptable quality for all of them. Now, what do these three tricks have in common is that if you have a positional representation like this, where the value of the number comes from a weighted sum of different positions, you find a factor of those weights. In this case, s is 2 to the 128. And the representation is chosen such that modulo the modulus that you are considering, s is congruent to a c that is small in some important sense. Thus, every occurrence of s in those weights can be replaced with a c. And in the special case for s is just a small number, thus we have our 4-position number reduced to a 2-position number, where the value of each position is slightly increased, but the overall representation is already smaller than before, which is exactly what you want to keep doing efficient arithmetic on these numbers. Now, I'll show you how this standard trick is encoded in fiat cryptography. I'll show you code. Please take a look at this code in the sense of what kinds of operations we use to express these algorithms. It is not important to follow every single line, and while I will narrate it at a high level, it is mostly on the screen to be shown how small it is. First, we define big numbers. They're lists of pairs of weight at that position and the value being stored. Then the evaluation of a positional representation is to take the dot product to scale each position by its weight and add them together. Multiplication simply multiplies each pair of positions on one number with each and the other number, so the weights get multiplied and the values get multiplied. To define division, we would really want an operation that gives us, if we divide by s, we would want a part that was divided by s and is the quotient, and then a remainder. If we had division, we could define reduction modulo m by doing division by s, taking the part that had a factor of s and replacing that with a factor of c and adding the remainder back in. Now, actual division is hard to implement, so we implement weak division that returns a remainder that may be larger than s, but is still small in some informal sense. And it's actually really important that we don't need to make formal how small c is, because we want to apply this template in 3 different cases where the smallness is different.
Sorry if this is getting too much into the weeds or if it was already clear. The weight and value thing for big num is surprising to me. I would expect to see like a list of limbs or something, most big number representations.
So the second components of my list are those limbs. We just the values, and we keep the weights present at compile time to be able to write the template in a generic manner. For example, the division algorithm that I have here, 1, 2 to the 32, 2 to the 64. Is how the limbs represent the overall number. And we can then programmatically access those weights to be able to express this division template in a generic manner where it calculates on those weights as opposed to having implicitly somehow guessed the right position for the right weight. Wow, this is limbs. Limbs is what people say when they have groups of digits. So you have binary digits, that's a 26-bit number. Now you use two 26-bit numbers to represent the bigger number, then those groups of bits are limbs. And the code on the slide is actually proven correct in less than 100 lines of code against specifications just like what are on the slide. I'm not going to show the proofs because they're not interesting. But what is interesting is that you can then take this general implementation and plug in concrete parameters. For example, weights being powers of 2 to the 51 gives you the standard implementation of curve 219 on a 64-bit computer. Weights being powers of 56 gives you a possible implementation of a different common cryptographic prime. And then to do something really challenging, which was a result in its own time when it was published independently of formalization, you can assign weights that are not powers of the same number. You could put 26 bits in the first position and then 25 bits in the next position and so on. And all of these templates still apply. Multiplication sometimes has scaling factors that are not obvious from the formula as shown. But you can still generate code that, in this case, runs efficiently on 32-bit processors where you can multiply two 26 or 25-bit numbers and get a 64-bit result. Now, just to see what that case looks like in more detail, we would have 10 positions, these alternating parts of weights, 25, sounds like 25.5 bits per position, almost. And to generate that implementation, we specialize the template to the primes, given separately as the power of 2, that is S, 2 through 255, and then the difference, which is C. In this case, it's a single position number with weight 1 and value 19. We have multiplication. We pass in lists of 10 positions, each of which gets assigned a weight by the weight function that I'm alighting here. And now this program that is on the screen is all you need in some sense. But to actually make it fast, all the loops get unrolled. The 10 positions are generated each their own specialized code. And on this pathway, there is really a certified compiler that does first partial evaluation. It takes functional programs and reduces away all pattern matches on lists that are known at compile time and so on. And then a library of rewrite lemmas gets applied to speed up the program. There are simple arithmetic operations similar to what LLM would do, but they all get applied on mathematical integers. And the next step is to perform abstract interpretation on the individual values over the positions of our big num and generate machine integers that are appropriately large to fit that number while still being performant. Now, I will not go into the details of this approach. There's a separate paper that discusses this. If you're interested, you can look it up. It says a lot of things about different formal compiler approaches that we considered for this purpose and how it was quite interesting to find the combination that actually worked for us. Instead, I will show you the code. Here's just a random page of this. It looks opaque. I will assure you, expert-written code also looks opaque. But you can kind of see that there's a 10 by 10 table, which is a school book multiplication of 10 lim numbers. And then there are some additions below. At the top of this code, we have a function header that you can just include into a normal C library and thus allow for easy adoption. But in particular, we have the specification at the top of our function that actually is generated from the Coq theorem we proved about this function. In this case, it's just something really simple. It says you can evaluate the arguments or you can evaluate the result, and they're related in the appropriate modular manner. But also for advanced usage, where this function might be used on its own, the bounds checked by abstract interpretation are also provided so that, in this case, multiplication can be applied arbitrarily many times, and it always satisfies its own input bounds. But there are cases where more delicate specifications are sometimes desirable. Now, if you benchmark this code, the picture you roughly see is that it runs as fast as other C code that people would write, but you can do even faster with specialized assembly code, which is what I will talk about next. The pipeline I have so far covered starts with functional templates, and
That number is what? Oh, CPU cycles. So
CPU
it's not
cycles.
a specialized assembly
Yes. And
on a Broadway.
yeah, it's a particular platform. It's in the field cryptography paper. The details are in there. And steps so far are functional programs. You pick some parameters, you do specialization and range analysis, and then there's low-level optimization, which I will go into now. But first, well, there have already been some good questions, but if there are any more right now about the part so far, I would take them.
How does this affect cryptographers' ability to do design space exploration?
We have seen companies doing unconventional cryptography designs using field cryptography as their first and sometimes only implementation. So I think they appreciate it.
Are there any sort of designs that people would not have been confident enough to explore without, like, you gave the example of the different, limb ranges or some kind of combinations that people wouldn't have tried otherwise?
We have definitely tried crazy stuff that we haven't seen others try before. However, the main place where we'd really try to make a big difference is producing a production quality implementation. Because producing a prototype implementation that does arithmetic right most of the time is vastly simpler than producing a highly vetted, highly audited, reliable implementation. And I wouldn't be surprised if there's something out there that was done with field crypto that wouldn't have been done before. It seems desirable in that regard, but I don't know of a concrete example. Now, moving on to automatic optimization. It's a part of the pipeline that acts after the original field cryptography part. So we take the generated code right before printing it into C. Instead, we feed it into an optimizer. What the optimizer does is that it first generates some silly code and then performs trial and error mutations, where it either takes two instructions and reorders them in a manner that preserves data flow. It uses a different x86 instruction to implement the same high-level operation, like addition, or it changes the register allocation decision at the output of a particular operation. So these are all optimizations that standard compilers do, but in this case, they're applied randomly in a closed-loop performance measurement setting so that we don't need to have heuristics that capture the performance behavior of the CPU.
How many different mutations did you implement?
I mean, if those are the three kinds of categories, then we would say 3. They actually break down into many smaller cases in implementation. This captures it at a high level. What does the performance profile of something like this look like? Well, the first generated code isn't even as good as C compilers, which are represented by the horizontal line here. But if you run it for thousands or tens of thousands of iterations, it catches up with C compilers. It then surpasses them in achieving performance beyond what we know how to achieve with any compiler.
Quick tangent. Are you worried at all about things like side channel attacks or things that can't be verified logically through Coq?
We are using standard engineering techniques to avoid side channels attacks. I am also currently working on verifying the lack of side channels through Coq. Yeah. Now, putting this performance experiment in comparison, we get code that is generally on par with assembly code that humans would have written by hand. If you let it run a good long time, then you might get an inch better, but it is a tool to achieve high assurance without compromising performance, which is why the industrial users appreciate it. Now, of course, the last optimization step is a highly performance-sensitive process itself. So instead of using Coq to do the optimization, we have an optimizer that runs, and then we write the checker, and we prove the checker correct in Coq. So when you feed the assembly code back into the checker, it hopefully says yes. Well, it mostly says yes. When we first ran it, we sometimes found it say no, and these errors corresponded to issues we had found in the optimizer itself. But given that the checker is proven correct against the model of x86, we are confident that the generated code is actually working as desired. The other aspect here is that you can use this checker to check manual optimizations. Here I took a popular implementation of arithmetic modulo P256, and they replaced an instruction that was an LEA, which is x86 were adding without setting the carry flag, and replaced it with add, which is adding and setting the carry flag. And this broke the implementation because the carry flag was storing some important information in there. And our checker gives us a detailed report of every place where the error might have been that caused this discrepancy. As with arithmetic it is not always obvious which location the error actually was, because the same machine registers could represent numbers in multiple ways. But here, actually, the last one that it points out is the correct location of the error. To achieve this kind of performance and predictability for interactive use, we needed to use relatively simple verification techniques. In particular, we needed to generate error messages that are at least somewhat useful. I know they're not at the level of the Rust compiler, but they're much better than what you would get from a very powerful verification tool. And thus, we do symbolic execution to turn the assembly program into a data flow graph. And then we canonicalize those data flow graphs using a system kind of similar to eGraphs, but it's almost a degenerate case of equivalence class graphs because we only keep a single representative of an equivalence class, and we chose the rewrite rules so that we always keep the correct representative. And this made the system very easy to use. Now, using these optimization capability, we were actually able to deploy more highly optimized implementations than were in use before. So this is in the Chrome web browser, where previously a less optimized implementation of P256 was included for reasons of having confidence in its correctness, even though faster assembly code was available. But with Fiat cryptography and CryptOpt, we were able to generate faster assembly code that did meet the confidence bar for being deployed in Chrome. There are other projects that do cryptographic arithmetic, and they have substantially inspired Fiat cryptography. What Fiat cryptography is really unique about is that we automate a very large part of this process. We don't only verify experts did an assembly or something very similar to what experts would have written. We actually perform the process and verify the process, which means we get push-button code generation, and we still maintain high performance. And the proofs are actually simpler at the level of those generic functional programs, just because the functional programs in their structure capture why the technique itself is correct at all. Now, at an even higher level, what we did is we studied what experts did and how they did it. We formalized this part, and we perhaps mechanized the most important part that was never said, which is that for each new prime, you can write a new implementation that is as fast. The same techniques actually do generalize. It is not just a one-off error that for each of those cryptographic primes, we had a fast implementation. And we mechanized this unsaid conjecture. And by doing so, the proofs are really easier than any other proofs of comparable code that have been out there. This is a very valuable benefit from this study. But also, we learned something about how to build rewriting systems and optimizers in a proof-checking context, but these are not details I will go into today. Now, I would take any questions about the low-level optimization part before I move on.
Yeah, I might have missed this earlier, but are all of these operations single-threaded, or are you also proving correctness about thread safety?
These cryptographic operations are so small that all the popular implementations are single-threaded, both ours and competitors.
Are there any mutations that your experts used that you did not encode? Any optimizations, I say that you did not encode as a mutation, I should say.
We encoded some optimizations in the high-level templates instead, and there are implementation targets we have not considered. But within the space of what we studied, we are on par with the kind of stuff that experts do.
Your mutations are all like preserve semantic equivalence.
They're intended to, but the optimizer is very complicated, and there have been cases where we ran the checker on the output and then realized the optimizer itself didn't do this.
So we told you we read your paper for our reading group last week. One of the questions that came up was, why, if you have a checker, why not just not preserve semantic equivalence, like Stoke style, and just have a bunch of mutations?
We tried running Stoke on their examples, and we couldn't get it to grok the size of the examples we had. And in general, like we're talking about programs that might be thousands of instructions long. Accidentally happening onto a correct implementation seems very unlikely. At very least, there should be a heuristic reason why these mutations would be desirable. Maybe there are interesting things to try that don't always preserve correctness, like intentionally try as opposed to accidentally try, but we haven't found that particularly attractive one yet. Now, moving on to a totally different topic, integration verification. This is all about proving that systems work correctly, given that their components were proven to work correctly. So in Fiat cryptography, we saw a little bit of this, a taste between the compiler passes and the software itself. But really, I'm thinking of this on bigger systems, like a bare metal network stack running a web application serving end users. And the reason we want to do integrated verification is that the gnarliest bugs appear at interfaces between components. Buffer overflows are a disagreement between user programs and the C compiler, and so on. And from a verification perspective, we also want this so that we can do modular proofs. We don't end up proving everything together because it is harder. And the biggest question, actually, that I have been spending a lot of time thinking about, that I want to tell you about, is what it makes sense to prove, because there are differently satisfying and dissatisfying answers to this question at different levels of the stack. And then I will tell you a little bit about the demo we did and the omnisemantics technique behind all of this success. Now, Interface confusion are behind big failures. I will give you a couple of examples. First is buffer overflows. If you overwrite the return pointer in a program, arbitrary badness can ensue. This is probably relatively well known. There is also more subtle examples, like when AMD added the sysret instruction to AMD 64, it was meant to enable faster return from system calls, and Intel added a similar instruction intending to be compatible, but it turns out that there were subtle differences in what the two vendors' instructions did, and thus software written for AMD processors was actually critically insecure when run on Intel processors for a while. This instruction fell out of popularity as a result of this difference. A different pragmatic example from cryptography implementation is that there are different dynamic rules in the kernel space and user space for how a program must use its stack. In user space, in Linux, the program is allowed to use 128 bytes past the stack pointer. In the kernel space, it is not, because the processor uses the same space for storing the interrupt context. And thus, if you try to be clever and benchmark your cryptographic implementations in kernel space to avoid context switching overhead, you might instead crash your computer because the dynamic contract is different. And notice this is really subtle. The API is the same, the instruction set is the same, and sometimes it even runs, but the contract is different, and it is fully in the right of the operating system to go wrong if you misuse it in this manner. Now, from a security perspective, however, for whole systems, there is a really nice saving grace, which is that it might be complicated what we want our system to do. There's this fuzzy boundary. It is hard to pin down what is desirable and what is not. But the vulnerabilities are really far out from what the system might do. Nobody would argue that the buffer overflow was intentional or the system should have executed the code it just received from a network packet inside a cat picture. Instead, we might have this broader scope of things that are like not too bad if they would happen, but this might too be difficult to summarize. But what helps us is that there is space between those two lines. We can pick any specification we want that we can formalize. And as long as we manage to prove our entire system against this specification, we have ruled out the bad attacks. Here is a straw specification that very coarsely captures what a bare metal system might do. It speaks Ethernet, and it receives some packets, and it responds only when it receives a packet. Many systems satisfy this property. It seems very weak. How useful might it be anyway? Well, if the system had an arbitrary code execution attack, then the attacker would be able to upload code that sends packets without receiving a packet first. Thus, this naive and almost silly specification rules out arbitrary code execution attacks. And now, satisfying this specification most of the time wouldn't be enough. Then it might still be not satisfied when there is an attack. But if we actually have computer-checked proofs and we can check that this specification is satisfied all the time, then this specification is, in some sense, very satisfying in its simplicity almost. We don't need to know what the system does. Now, you would say, oh, but there are other bad vulnerabilities where you need to rule out more badness than this. Well, let's look at Heartbleed. OK, I'll first tell you about how I will formalize this spec, because that's apparently the slide I have now. To say the system responds only when requested, we can write the property like a regular expression. There's first the boot part, which we ignore, and then we say repeatedly there's a request and then a response. Not response, response, response. And to tie this to a concrete system, we need to have a model of our system. We say that if we have a machine code program, which we probably prove correct, and we place it in a memory, say at address 0, and then we take a verified processor and consider possible I/O traces of that processor. So T here is an I/O trace. Then this trace predicate above should hold on T. There's a catch. Your observation might stop in the middle of a network request, in which case the trace predicate as shown doesn't hold. So we allow a little bit of leeway. We say the trace must be extensible to a trace that satisfies the predicate above. But here is a system-level specification of this property that is captured in its all essential parts on the slide. And we actually proved something like this. And to prove this, we needed much more complicated specifications on the way towards this high-level result. For more subtle vulnerabilities, you need more subtle specs, but often only barely more subtle. So if you want to rule out arbitrary information leakage, we'll say what the system responds in the packet. We'll say, OK, it boots up, and then it receives a connection, and then it picks a cryptographic challenge to authenticate the user. It sends that challenge in particular, not arbitrary bytes, that challenge. And then either it receives an authenticated packet and performs the command that authenticated against that particular challenge, or it receives something that failed authentication, again, with respect to that particular challenge, and it moves on. Now, in the 2 experiments we performed with integration verification at scale, we verified 2 systems against specifications that are very similar to the two that I just showed. First, we proved the software and hardware system from I/O specs to a hardware description language, just an example was formalization I showed. And then we proved the cryptographic system that includes all the same stuff as before and via cryptography. The optimized cryptography implementations we generate from high-level templates against the specification that relates RISC-V machine code as the bottom interface to IO specs as the top interface, doing cryptographic challenge response authentication with public key cryptography. I will not go into the details of how this proof works today, but I will tell you about the key trick that made this possible. In the context of other systems, the really new part here is that we verify I/O. Our specifications talk about interactive input that might be received incrementally throughout the execution of the process, and then specify the responses to that in a relational manner while allowing for complicated optimizations inside the system. So you could have various techniques that apply either without I/O or either for systems that can be verified without abstraction. But if we have optimizations, we need abstraction, and thus we need a modular proof technique like what I'm just going to discuss next.
So you're only verifying the interfaces itself, not the implementation code in each
Both.
of those? Both?
Yeah.
How many lines is it?
Lines of what?
Code that you're verifying?
If you include the if you exclude the hardware, it ends up being a couple thousand in this stack. But the implementation verification is not the part where we innovate. It's the interfaces that are behind our new results, and we intentionally picked simple implementations between those interfaces to make our work tractable. Now, we actually did a demo where we had cryptographic authentication open a garage door when we responded. Now, so I can show people what I did but, without going into pages and pages of Greek letters. But we built a demo to show off the system. It is really the interface specification styles that are the contribution in this work, and then showing them off with doing a canonical stand-in task for what an industrial control system might look like in the evolution of this work is a neat way to show it off, but not the core technical content. Now, okay, questions? Great. The next part is really technical, and I will go into making specific claims about verification techniques. So if you want to discuss anything about what we're trying to do, let's do this now. But I'm going to dive right in. Omnisemantics. It's the technique that made these integration verification tasks possible. And in particular, it is about ruling out bugs at the interfaces themselves. It is not fine to verify two components separately because you could have separately specified them in a manner that is incompatible. And thus, we need an interface that satisfies needs of both components to do the verification. And the reason why internal interfaces are so much more challenging than external interfaces is that there are mutual requirements. It is not just that the system does the right thing, it's that the C program does the right thing, if the C compiler does the right thing, if the C program does the right thing. And thus there is no easy way where you can draw a round line and say like, oh yeah, somewhere here is the spec we want, any of these would do. In the language of formal methods, the challenges are about unspecified behavior and undefined behavior. These are different concepts. I will show them what they mean in the example of simple C constructs on the next slide. But it is famous that these things are challenging to formalize in a satisfying manner. There are very precise formalisms that are very hard to work with, and limiting formalisms that then sometimes are accompanied with advice to not do anything that falls outside of those limiting formalisms. Now, in a C program, you're going to have a buffer overflow. It's perhaps the most dangerous kind of vulnerability that is still widespread. And if you write past the end of an array that your program is allowed to access, then you might be overwriting really important stuff like the next piece of code to execute. In this case, we say the behavior is undefined because if your program does this, there is nothing reasonable the compiler could do to help you. It can't even produce a reasonable error message because the code that it executes might be overwritten. We can then also ask the question of, what if you print the address of this array? And in this case, we say the answer is unspecified because the compiler in its stack allocation phase might have picked any offset from the stack pointer it chooses, and your program must work correctly in any case. But just because your program depends or even produces output that is dependent on this unspecified part, it is not invalid. It is simply having more than one permissible behavior. To formalize these two notions in a manner that they play nicely together, we used omnisemantics. Omnisemantics are an alternative to traditional operational semantics that maintain many of the advantages while allowing for easy mixing of undefined behavior and unspecified behavior. I will just give you a couple of examples of how this pans out. In both cases, we relate the program and the starting state to something about how the program terminates. In the case of traditional semantics, we give an individual final state as an argument of the relation. In omnisemantics, we give a set of possible final states. This doesn't mean that traditional semantics can't encode non-determinism. They can, But the way that it is done is that you say your program may execute to one state or it may execute to another state. And I would argue that this is already counterintuitive. A human might say that this program produces A or B, not that it possibly produces A and it possibly produces B. And in fact, in omnisemantics, the appropriate postcondition exactly is a set of two states. And if you look at how a set of two states is encoded in a proof assistant, it is the set of states that are equal to one or the other. So this program runs to S1 or S2. Further, if we now consider the possibility that one of those possible executions triggers undefined behavior and something goes wrong, the two approaches in their natural application differ drastically. If we add a crashing execution in one of those cases, omnisemantics just no longer applies to this program. You can't prove any fact of the form this program runs to blah using omnisemantics. In traditional semantics, one way you could formalize, you could still prove something about the possible good execution while losing all information about the bad execution. So you would need to add that back somehow to rule it out. And that can be challenging. In particular, it can be challenging to even define what it means that a program always executes correctly using traditional semantics when you have possibilities of non-termination and undefined behavior. And the property we really want is that all possible ways this program could run, they terminate, they don't crash, and they satisfy the desired specification. And you can state it using traditional semantics. There is a complicated formula on the slide. But instead what people do is they say, OK, we're OK if our program doesn't terminate. As long as it terminates, when it terminates, we prove that it's good. And this is, for example, what the Princeton verified software toolchain does. It is a satisfying choice from a formal methods perspective, as many of the challenges that are there for verifying correctness given termination are also there for verifying total correctness. But with omnisemantics, the notion naturally encoded in this judgment already is the total correctness you would want for a real deployable system. And it is this reason that shows up even more drastically in compiler verification. So if we want to prove that our compiler in the bottom layer of our stack correctly compiles programs, we might look at the simple case of optimizing a program where the target language and source language are the same. And then with omnisemantics, you can say that if the source program, P runs to Q, then the target program also runs to Q. This is a statement that in some sense comes naturally, and further you can prove it by the most direct method of proof that is applicable, which is translating every possible source execution into an appropriate target language execution. Experts of compiler verification in the audience might be looking weird at me and thinking that this is not how it is done, because with traditional semantics, there's this notion that is called backward simulation that everybody tells you that you need to prove your compiler appropriately. And the name has backward in it. It is a little bit counterintuitive. It was a finding that this is necessary. But the intuition is that even though your target language has one good execution, just showing the existence of one is not enough. You need to show that it can't go wrong, for which you need to consider all possible target language executions. So the statement there really starts by saying, consider how the optimized program ran, and then try to prove something about the source program. But this is really challenging to prove, because if optimize returns many small instructions for a simple input program, you're just doing hypothetical considerations over low-level programs that might be much larger, and it gets very tedious very quickly. So instead, what compiler verification projects like CompCert do is that they say, oh, we can actually make this problem simpler if we restrict the possible behaviors in our programming language. Specifically, CompCert does not have a genuine notion of unspecified behavior. It is surprising. C looks unspecified in many ways. But CompCert plays this game where executions that would trigger genuine unspecified behavior are themselves undefined instead. And this limitation in semantics allows them to replace backward simulations with a much more feasible proof technique that arguably is behind the success of CompCert at all. Now, it also has small downsides, such as trying to prove the standard library function memmove, which takes 2 pointers, and in the canonical implementation, as the first thing, compares them. There's a question of, well, if those pointers are allocated on the stack, it is up to the compiler which pointer comes first. And thus, this branch might go left or right, depending on compiler choices, and is genuinely unspecified. But either way, this function would do the right thing, so we should have correctness here. What CompCert says is, you're not even allowed to ask which of those pointers comes first. Pointers are opaque. Pointers to different blocks are only known by their block ID. If your 2 pointers are not in the same block, comparing them is not allowed. And this simplification was very critical for CompCert working, and it comes at the cost of this counterintuitive behavior.
On the other hand, it allows you to have a very loose set of requirements on the allocator, right?
So there's a lot of allocators that can be plugged into COMSORT and be compatible with COMSORT's set of assumptions in the allocator. With omnisemantics, it feels like there's some fundamental tension between specifying the details of the allocator enough that you could do this kind of proof and, I don't know, being parametric over the allocator.
The specification of stack allocation in omnisemantics is that the compiler might pick any address whatsoever and initialize it to any value whatsoever. It is completely flexible.
So instead of just not having the relation for the semantics be inhabited, you just say there is something, but you don't get to pick what it is.
Yeah. The way it shows up from the perspective of the program proof is that you must prove the rest of your program under the assumption of a universally quantified allocation. And in the definition of omnisemantics rule for stack allocation, it actually calls the post condition under a universal quantifier. So it is an infinitary inductive definition that makes it work behind the scenes. Now, there's much more to omnisemantics than what I just told you. It has been used for type soundness proofs, lambda calculus stuff, even a hardware description language was prototyped using it. And we have been generally happy with this in all levels. In not all of those cases is it an improvement, but in some cases it's a huge improvement, like compiler correctness. Any questions so far?
Maybe there's not a good answer to this, but at first, when you were showing omnisemantics, I was just thinking, oh, okay, great, because your standard non-determinism approach, we're going to have, like, you're going to transition from a state to power set of states, or like a set of states. That makes perfect sense. It seems like there's something more to it. Is there's something more to it precisely about like the handling of errors and these like I guess undefined behavior, the other sorts of exceptional states.
So generally when people talk about modeling non-determinism using power sets, it is more often in the context of verifying programs written in the language as opposed to verifying compilers for that language. The thing that makes omnisemantics unique is that it forms the appropriate specification of that interface for using both sides. When we give an omnisemantics judgment about the program, it is useful both concretely, applied to a particular program, and abstractly when the program is not known. And to give this definition, yes, it is, in our opinion, a key feature of omnisemantics that it enforces safety of all possible executions as part of the same judgment that determines the semantics. This is something we could discuss in more detail later. There is space for iteration there. Now, I will say a little bit about future work. And, well, apparently I have a slide here about what is behind omnisemantics. And it's the same idea. Is we take how experts specified their systems. We look at what the actual desired behaviors that, say, OpenBSD developers have for the C language and try to encode them precisely, and as opposed to taking formalizations.
Use any particular method there?
It is very informal. It is talk to people and see how they talk about their code. Read their mailing lists, read their bug trackers, try to work with them, see how they bounce back when you try to tell them about your formalization of C as abstract pointers. And it's hard. Like, if I were able to give advice on this, listen more than talk is probably the most generic advice that is relevant here, and I think a lot of formal verification work could benefit this in more generally. And it is in particular the things that neither community has words for that are the biggest gaps that are very valuable when they're bridged. But then, once the right formalism is found, doing a really challenging compiler proof for stack allocation, which we thought would be a very challenging feature based on experience from COMSORT, actually turned out really well. And again, the same technique we developed for the specific case of low-level language compilation was then applied more broadly. So we learned something about not just how to do that system, but how to verify systems more generally. In future work, I would like to expand this overall stack to actually care about doing work in adjacent situations and making them work well together. Understanding how the integration part pans out is perhaps the most satisfying and most informative part of the specification research itself. And in particular, I would like to deal with the limitation of current specifications that our system has about side channels. There are two kinds of side channels we're considering. There is side channels that might be made worse by the compiler and side channels that might be made worse by the processor. In general, in both of those cases, we take the perspective that we want to protect the program from attacks over the network as a stepping stone and perhaps capturing most of the complexity towards protecting one virtual machine from another or so on. And we would then like to wrap this up into a proof of cryptographic security that, if stated at a very low level, inherently needs to include a proof of side channel security, because if your model of the network is bit by bit, and the timing of those bits on the Ethernet wire matters, you can't just write a spec that is except for timing attacks. Yeah. If you want to state it at a sufficiently low level, timing and output are the same thing. And to build this, we really need to also build more proof engine tooling. So we need to probably find a way to finally bridge SMT solvers and interactive theorem proving stuff in practice. It has been an active research topic for over a decade, and so far we have been making do without those tools for practical reasons. Perhaps a thing that could be helpful there is a common IR for efficient interchange of proof calls between very different proof procedures. The success of Coq so far arguably is based on their proof engine representation already, but based on that experience, I think there's a lot that could be improved, and lambda DAGs in particular might be a nice representation to try, in that they correspond to LVM-IR in the first order case, which seems rather good of an intuition.
What's a lambda DAG?
It is a DAG where inside lambda nodes you have more DAGs. And in the very low-level language land, we would like to use this to do symbolic execution of programs that do address arithmetic and handle aliasing between their arguments. And there are specific application domains for which we would like to have bare metal implementations of them to build towards our larger system, and again, to meet the guarantees required for industrial applications and continuously maintain production deployments throughout the development of these components into a larger system. I am happy to tell you more about our side channel work, but if there are any questions that are right on the top of your mind right now, I would take them as well. Okay, side channels between compilers. So in cryptography verification, there's this concept of constant time programming, where you essentially make sure that your branch conditions and memory access addresses do not depend on secrets. It's been very successful in cryptography, a little bit applied more widely. But it is a little bit subtle how to even specify this notion for a non-deterministic language separately from the compiler, because if you have an address that is allocated on the stack and you store to the address of that object, the question is, well, is that address secret or public? Can I prove that I didn't leak a secret by storing to the address I just allocated? And in practice, you would expect this to work out because the compiler picks this address based on a stack pointer and not based on values of other variables in your program. But even that is only safe because you are not allowed to branch on a secret. If your instruction pointer depended on secrets, then your stack pointer would depend on secrets, and then this rule would not work out. And jumping back and forth between those true worlds for this argument, we can say, like, yeah, all of this works out nicely. But to be able to do a compiler proof for all possible programs, we would need a specification that captures this notion. And in some sense, we would want to say that every time you branch on something, it is public, and thus you get to assume that the addresses the compiler allocates are public. But actually formalizing this is an open problem as of the state of the literature, and while the case for a deterministic language has been demonstrated on a number of passes from CompCert, we are currently working on defining the appropriate notion of compiler correctness and the appropriate notion of semantics for preserving data flow across the non-deterministic interface. And this work is decently far along. We have 4 definitions. We have proven 2 of them equivalent. We believe the other 2 are not equivalent. Probably we'll figure this one out. Things get even more challenging if you talk about side channels with processors, and this is where people are worried about cross-VM attacks a lot. But I'm still going to take the perspective of network attacks, which are still applicable in that setting, and ask, could we use the prospect technique for mitigating side channels, which is essentially making the processor know about what is allowed to be leaked and what is not? A way you could think of this is not quite what the prospect paper does, is to say that for each piece of memory, instead of having read, write, and execute bits, you have an additional leak bit, which says whether it is fine for this piece of information to be leaked through speculation. Then the processor will limit speculation based on that information. But to add these bits to your program state, we need compiler support. In particular, currently the prospect worked was evaluated on programs that were first compiled with the off-the-shelf C compiler, then modified for the purpose of that case study. And of course, this is not a way you can prove a system-level theorem. So what we would like to do is we would like to build a compiler that, with appropriate level of programmer help in relatively constrained parts of the program, appropriately spills, for example, secret variables to one part of the stack and public variables to another part of the stack, and thus satisfies the requirements of prospect. And there is a compiler design effort, there's compiler verification in the process, and the cool thing about this technique is that it should then be possible to scale the same idea to even more advanced processor features, and both do use cases where the attacker and defender run on the same machine or over a network. Thank you.
All right, thank you so much. I think we have time for a couple of quick questions. Maybe to launch things, I'll give you an easy one. So in the omnisemantics, how do you deal with non-terminating executions? Do you have like co-inductive traces as part of the set of things a program can step to?
We are working on that. The current systems I showed you use omnisemantics for the terminating parts of the program, and the top-level event loop is separate from that. We can also specify divergence or that the program is non-terminating. Achieving the full construct equivalent specification preservation for arbitrary traces is ongoing work on an open problem.
Thanks. That was really fun. So one of the challenges, especially with some of the last stuff you were talking about with the microarchitectural leakage, is that you end up in a situation where you have you are fine for the semantics of your program, even potentially for threads and whatnot. But if you care about where you spill stuff, because you're talking about spilling things to secret and non-secret stacks, interrupts become incredibly nasty. And so this is a great example, I feel like, of where your interface stuff that you were talking about. Is this solvable?
I do not know about that specific case.
Okay. So the challenge is that essentially if you care about where you spill secret and non-secret data, if you take an interrupt, the kernel needs to know about where to spill your secret or non-secret data. Your program might be perfectly capable of doing this, but the kernel may not be aware of that. And so there needs to be a cross-privilege level awareness of the challenge.
Yes, I believe that is true, and I believe my intuition here is that the privileged bits that are presented to the processor should also be context switched by the kernel. Maybe that's all you need. Just thinking on the spot here.
We can talk about this offline as well. I was just curious if you had any insights. Thanks.
Any last questions? All right, thank you so much. Let's thank Andres once again.